On December 27, 2004, a wave of invisible radiation swept through the solar system, instantly blinding several astronomical satellites and physically altering the upper atmosphere of the Earth. It did not originate from our Sun, nor from any neighboring star system, but from a dense remnant sitting 50,000 light-years away on the far side of the Milky Way galaxy. In a fraction of a second, this distant object released more energy than our Sun produces in 250,000 years. Had this event occurred within 10 light-years of our planet, it would have wiped out the ozone layer, triggered a mass extinction, and permanently altered the course of terrestrial biology. This cataclysmic pulse was the calling card of SGR 1806-20, an extreme stellar corpse known as a magnetar, which possesses the most intense magnetic field ever recorded in the known universe. To understand SGR 1806-20, we must look to the constellation of Sagittarius, deep within the dust-shrouded core of our galaxy. Discovered initially in 1979 as a soft gamma repeater, a rare class of stars that emit unpredictable bursts of high-energy radiation, it spent decades puzzling astrophysicists who struggled to explain its erratic behavior. It was only in the late 1990s, through observations made by space-based telescopes like NASA's Rossi X-ray Timing Explorer, that its true identity was revealed. SGR 1806-20 is not a standard star, but a neutron star born from the violent supernova of a massive progenitor. When a star with up to 40 times the mass of our Sun runs out of nuclear fuel, its core collapses under its own immense gravity. While the outer layers are blasted into deep space, the core is compressed into a sphere just 20 kilometers in diameter. SGR 1806-20 is a hyper-condensed ball of pure neutrons, packing a mass greater than our Sun into a space smaller than a modern metropolis. The physics governing SGR 1806-20 defy ordinary comprehension. If you could somehow harvest a single teaspoon of its material, it would weigh over 1 billion tons on Earth, equivalent to the mass of a large mountain. Yet, its most terrifying attribute is its magnetic field. While a typical refrigerator magnet has a strength of about 100 Gauss, and the Earth's protective magnetic field measures just half a Gauss, the magnetic field of SGR 1806-20 is estimated at an astronomical 100 trillion Gauss. At this unfathomable intensity, the laws of chemistry and physics break down. If your body were to venture within 1,000 kilometers of this magnetar, the sheer strength of the magnetic field would instantly dissolve your physical form. The field is so strong that it distorts the electron clouds of your atoms, stretching them into microscopic, needle-like shapes. This instantly breaks all chemical bonds, causing your body to disintegrate into an atomic mist, long before you even touch the solid crust of the star. Even empty space near the magnetar is altered, as the vacuum itself becomes polarized, split into refractive indices that bend passing light in a process called vacuum birefringence. The surface of SGR 1806-20 is a hellish landscape of extreme forces. It spins on its axis once every 7.5 seconds, a dizzying speed for an object of such immense mass. Surrounding the star is a solid crust of crystalline iron, compressed to a density billions of times greater than steel. Because the magnetic field is anchored deep within the star's interior, the rapid rotation twists and wraps these magnetic lines of force into a tangled, high-tension knot. As the field bends, it exerts a monumental drag on the crust. Eventually, the solid iron surface reaches its breaking point. When the crust fractures, it triggers a cosmic phenomenon known as a starquake. Even a tiny rupture of just a fraction of a millimeter releases a torrent of energy. The sudden shift snaps the magnetic field lines, unleashing a blinding fireball of gamma rays and electron-positron pairs that expands outward into the void at nearly the speed of light. This is precisely what happened during the 2004 giant flare, producing a flash that temporarily blinded several satellite detectors and compressed the Earth's magnetosphere. Yet, despite decades of study, SGR 1806-20 continues to harbor deep mysteries that challenge our understanding of stellar evolution. Astronomers still do not fully comprehend why certain supernovae produce ordinary, quiet neutron stars, while others spawn highly volatile magnetars. Some models suggest that the progenitor star must have been spinning exceptionally fast before its collapse, driving a dynamo effect that amplified the magnetic field to its extreme limits. Others propose that binary star interactions play a critical role, transferring mass and angular momentum to create this magnetic monster. There is also the question of the magnetar's lifespan. Because they radiate energy at such an unsustainable rate, magnetars are thought to have extremely short active lives, lasting perhaps only 10,000 years before their magnetic fields decay into quiet obscurity. This means everything we observe of SGR 1806-20 is a fleeting snapshot of a cosmic blink of an eye, a temporary state of high-energy chaos in a galaxy that is billions of years old. The study of SGR 1806-20 forces us to confront the sheer scale and hostility of the cosmos. Everything you have ever seen, felt, or built exists in a fragile pocket of calm, shielded by a gentle magnetic field and vast cosmic distances. SGR 1806-20 serves as a stark reminder that the universe is governed by forces capable of warping the very fabric of matter itself. As astronomers continue to monitor this silent, spinning beacon on the far side of our galaxy, we are reminded of our own vulnerability, and of the incredible, extreme environments that exist just beyond the horizon of our night sky.